Have you ever wondered if gravity operates under the strange rules of quantum mechanics, like particles that can be in two places at once? Or does it remain the classic force described by Einstein's general relativity? This profound question has puzzled scientists for decades. Today, we're exploring a groundbreaking proposal by researchers Farhan Hanif, Debarshi Das, Jonathan Halliwell, Dipankar Home, Anupam Mazumdar, Hendrik Ulbricht, and Sugato Bose. They've devised an experiment that could finally reveal whether gravity is inherently quantum. In the quantum realm, the world of the very small, particles don't behave like objects in our everyday experience. They can exist in multiple states or places at once, a phenomenon known as superposition. They can also become entangled, meaning the state of one particle instantly influences another, no matter how far apart they are. We've successfully merged quantum mechanics with three of the four fundamental forces of nature: electromagnetism and the strong and weak nuclear forces. But gravity, the force that governs the motion of planets and galaxies, remains the elusive outlier. Einstein's general relativity describes gravity as the curvature of space-time caused by mass and energy. It's a classical theory that works exceptionally well on large scales. However, when we try to apply quantum mechanics to gravity, things don't add up. The mathematical frameworks clash, leading to nonsensical infinities. This has led scientists to wonder, is gravity truly a quantum force, or does it remain purely classical? Previous experiments aimed to detect the quantum nature of gravity by observing entanglement between two masses. If gravity can cause entanglement, it would suggest that gravity itself is quantum. But these experiments face immense challenges. They require isolating tiny masses from all forms of environmental interference. Even the slightest vibration or thermal fluctuation, collectively known as decoherence, can destroy the delicate quantum states needed for entanglement. Enter the new proposal by Hanif, Das, and their colleagues. Instead of trying to detect entanglement directly, they focus on a different quantum property, the unavoidable disturbance caused by measurement. In classical physics, you can measure a system without affecting it, but in quantum mechanics, the very act of measurement alters the system's state. This is not due to any imperfection in the measurement device. It's a fundamental aspect of how nature operates at the quantum level. The experiment begins with a tiny mass. Let's call it the source mass, that is placed in a superposition of being in two places at once. This is achieved using an interferometer, a device that splits and recombines waves or particles, allowing them to interfere. Initially, the source mass travels through the interferometer without any interference. We measure its final state, and since no measurement disturbed it along the way, we can predict the outcome with certainty. Next, while the source mass is still in superposition, we introduce a probe, a second tiny mass with an embedded spin and its own interferometer. This probe is designed to measure the gravitational field of the source mass without interacting through any other forces, like electromagnetism. In classical physics, measuring the gravitational field shouldn't disturb the source mass. But if gravity is quantum, the act of measurement should inherently disturb the system. This brings us to the non-disturbance condition, or NDC. In a classical system, performing a measurement shouldn't alter the outcome of future measurements on that system. If we find that measuring the gravitational field of the source mass changes the probabilities of its final state, we have violated the NDC. Such a violation would indicate that gravity behaves according to quantum mechanics, because the disturbance is unavoidable and inherent, not due to any experimental imperfections. to ensure that any observed disturbance is truly due to gravity's quantum nature and not a classical effect, the researchers used two probes in sequence. This clever design cancels out any predictable classical influences that could mimic quantum disturbance. Additionally, because the measurement-induced disturbance remains detectable even with environmental decoherence, the experiment is more robust and practical than those requiring the observation of entanglement. If the experiment detects a violation of the non-disturbance condition, it would provide strong evidence that gravity is inherently quantum. This could be a monumental step toward unifying quantum mechanics and general relativity, something physicists have been striving to achieve for nearly a century. Such a unification could lead to new physics, potentially revealing deeper insights into the fabric of the universe, black holes, and even the origins of the cosmos. The quest to understand whether gravity is quantum isn't just about solving an academic puzzle. It's about uncovering the fundamental principles that govern reality. The innovative experiment proposed by Farhan Hanif, Debarshi Das, Jonathan Hallowell, Dipankar Home, Anupam Mazumdar, Hendrik Ulbricht, and Sugato Bose offers a promising path forward. By focusing on measurement-induced disturbance, a cornerstone of quantum mechanics, they bring us closer to answering one of the universe's greatest mysteries. As we await the results of this groundbreaking work, one thing is certain: we're on the verge of potentially reshaping our understanding of the cosmos. This exploration was based on the research paper testing whether gravity acts as a quantum entity when measured by Hanif, Das, Halliwell, Home, Mazumdar, Ulbricht, and Bose. We thank these scientists for their dedication to advancing our understanding of the universe. Thank you for joining us on this journey into the frontiers of physics. Stay curious,